Good morning, everyone. Thanks for coming to my presentation. This morning, I'm going to give you a brief update on experimental research on Douglas-fir CLT for mass timber construction. As we know, CLT is now being widely used in New Zealand, Australia, and globally. It provides versatility and sustainability for building industry. Unfortunately, as a relatively new engineered timber product, CLT is not covered by the current New Zealand Timber Design Standard 3603, and also the forthcoming New Zealand standard does not cover CLT design. Therefore, there's a need to provide technical evidence to specify New Zealand-made Douglas-fir CLT into future timber design standard so that engineers will have confidence to specify this type of product. And also another great benefit really is to add values to Douglas-fir timber's resource in New Zealand by specifying and providing technical solutions of using Douglas-fir CLT for multi-story building design. My talk will briefly cover 5 parts, so I will give you a quick introduction of the current trend of building tall timber buildings, and then move on. We are looking at different testings to evaluate rolling shear strength, to understand the critical connection behavior in Douglas-fir CLT, and also to develop a low damage CLT wall system to resist earthquake load. And then last, I will talk about some conclusions. So a lot of people say CLT is a type of jumbo plywood, but the difference is plywood using thin veneers. In CLT, we use much thicker timber lamination, typically structured timber boards, and they laid up together in a crosswise way, and then we also apply adhesive on the wider surface so that they can glue and bound together. And at the same time, we need to apply pressure to cool the adhesive. So on the right side, I want to show this a Douglas-fir CLT panel with really a large size, 2 meter wide roughly, up to almost 6 or 7 meter long. So this is made the New Zealand Douglas-fir CLT, and you also notice that there are a number of cavities. We leave these cavities by leaving some boards during the manufacturing process. So the cavities are used to run post-tensioning tendons, steel tendons, to anchor the wall into the foundation. These 3 buildings are recently built. These are really one of those tallest timber buildings around the world, 18-story, 24-story, and 13-story. All these buildings used CLT as major structural elements. So particularly in these 13-story building, so it's 100% CLT buildings with glue lamp as the main structure components. So pure timber building, and the other 2 is a kind of a hybrid CLT with concrete, etc. So coming to New Zealand and Australia, we've built quite a few CLT buildings. So for Tay building on the left side is one of the earliest CLT construction in Australia and around the world. 10-story, 9-story CLT construction sitting on 1-story concrete podium, and 25 King, another timber building using CLT floor system. And on the right side, we've seen 2 multi-story buildings for residential application. So they all used New Zealand-made CLT products. I mentioned CLT is similar to plywood, having wood fibers oriented crosswisely, and in actual application, we have to be careful about rolling shear properties of CLT because sometimes it may govern the capacity of these panels. So we did some bending test and planar shear test really to derive the design strength for rolling shear for Douglas-fir CLT. So our testing result indicate roughly 1 megapascal as the characteristic rolling shear strength, so that engineers can specify these value in the CLT design, in the Douglas-fir CLT design. As I said, connection components are critical components in timber buildings, particularly under earthquake load. Connection behavior essentially governs the building behavior, because we know wood is relatively brittle material, so under earthquake load, it is not able to dissipate much energy. So essentially, connections are the source of energy dissipation for most of timber buildings. Therefore, in New Zealand, to design buildings, timber buildings, to resist high earthquake load, it is very critical to understand connections with a different type of fasteners, fixing types. So the first connection test we did is on the hold-on connections using big size dowels. So these hold-ons are critical component for a CLT wall to resist earthquake load. Imagine without this proper design of hold-ons, these walls are not able to resist any earthquake load or wind load, because these walls can be tipped over very easily. So in our lab, we tested different thickness of CLT panels, different sizes of dowels. The main purpose is to derive these load displacement relationships and to understand strength and stiffness, understand energy dissipation, and also we try to improve the connection details to achieve better connection behavior. We also looked at commercial hold-on design using these commercial hold-on brackets. So these type of hold-ons are not as strong as the previous dowel hold-downs, but they are cost-effective and they can be used efficiently for relatively low CLT structures. So this purpose, again, this test is to look at ductility and overstrength and provide information for design engineers to design wall structures using these type of hold-on devices. And the third part of the connection test is on the self-tapping screws. Okay, so we are looking at these proprietary product commonly used for mass timber construction. Most of them are European product, and their design document or equations are mainly derived from European CLT product using different species than the species in New Zealand. Therefore, this testing is to really verify those design equations and try to check those design parameters, see if they are also applicable to New Zealand Douglas-fir CLT. And then we move on to look at connection behavior using these long self-tapping screws. Again, we tried to improve the connection details to design stronger and stiffer screwed connections to connect these CLT panels in orthogonal directions. The last connection testing is on the conventional wood-to-wood carpentry joints. So without using any mechanical fasteners or steel plate, we try to understand the shear capacities of these carpentry joint. And we know we can follow some design equations to predict these castellated or carpentry wood-wood connection. However, we noticed that some design equations are okay in predicting the actual strength of the joint. However, in some circumstances, the predicted equations are very conservative, and we think there's a room we can improve the accuracy of those prediction equations to predict the shear capacity of these castellated joints. And Wall testing project, we put a lot of effort to test large-scale single walls, coupled walls, and flanged core walls. So the single wall and the coupled wall are typical wall setup in CLT construction, but the difference in our testing is we introduced a post-tension tendons going through the entire height of these walls, and these tendons will be applied with high post-tension forces. Therefore, it can bring these walls back under earthquake loading. So then we introduce additional connection types to dissipate energy. Therefore, we can really concentrate seismic damage in local area. And after big earthquakes, we can go do quick inspection and replace those damaged connections, for example. So on the right side, this gigantic bookshelf essentially is trying to simulate the lift shaft designed as critical core wall structures to resist lateral load. And we believe by having these returning walls incorporated into a shear wall design, we can significantly improve the strength and the stiffness compared with the single walls and coupled walls. And our testing result proved our concept of introducing these returning walls as part of the shear wall structure. So I'm gonna give you a quick video showing the last test phase on these core wall structures. We simulate earthquake loading on top of the wall by applying the forces along two orthogonal directions, and we basically track the amount of load and the amount of displacement, and then we derive the wall strength and stiffness and energy dissipation and ductility, etc. So these walls have been tested in many sequences of loading, and it performed very well, and we observed only local damage at the base of the wall, and we believe those damages should be easy to repair. And these are some connection details. We basically tried the different orthogonal joints between the vertical wall panels. And the last case, we showed the best performance by having these screws installed in different angles. And we believe we've achieved significant amount of composite actions. And that's why these walls behave much stiffer and stronger than the other cases. Here are some quick conclusions. And from our testing, we found Douglas-fir CLT provide superior structural performance for multi-story building application compared with light timber frame construction. And robust and ductile connection detail can be achieved in Douglas-fir CLT to resist high earthquake load. And proper designed low damage Douglas-fir CLT wall structure can significantly improve seismic resilience. And we believe these type of core wall structure offer a lot of more flexibility to CLT building design. And research is still ongoing currently. So we are looking at a different type of Douglas-fir CLT connections and different wall solutions to really provide different solutions to improve the structural efficiency compared with conventional solutions. These are the sponsors we would like to acknowledge. And also I want to thank our research team, student Justin Brown, Wen Chen Dong, Benjamin Morman, Thomas Wright, as well as a great support from our technicians. So this is the last slide showing great teamwork after the core wall testing was done. So really, I want to thank the great contributions from the students and technicians. And we pretty much also enjoyed this research project funded by SWP and other project funders. I'm happy to take any questions if you have anything want to ask.